the remaining inputs. And again, I define B on inputs in the set yk minus 1, so on inputs of length k minus 1, in a way, so what I want to get is that B on these inputs of length k minus 1 outputs the majority answer of that B produces on inputs of length k. In order to do this, again, let me define B so that it computes majority answer of AI on inputs of length k. And to do this, we use that majority amplification procedure. Okay? So consider outputs of AI on inputs of length k, it's a very long string of length 2 to the k, and we just do amplification of the most popular answer, of the most popular value in that string. Okay, and this part, well, maybe it's not very formal, and maybe there is a small mistake here, but something like this may be obtained from the assumption that AI agrees with B on more than half of inputs of length k. Okay? So the majority answer of AI is equal to majority answer of B.
So, wait. Point now, where is the definition of A?
Okay.
Where is the assumption?
The definition of B on these inputs is this.
Why
this input is this.
And why is it in NP then?
Why is that in NP?
Yeah.
Okay, here it's in P. Actually, it has to simulate deterministically AI.
On small string only.
On small strings, we have 2 to the n strings, and they are, and we have to spend on every string 2 to the n time.
And there we have no negation, and that's
no negation, and we have polynomial degree.
I see.
So this is why I had to use expanders, because we cannot just iterate over all possible inputs of length k. It would take exponential time. And this is from our assumption.
I see.
And together this gives this nice implication, and we have it for every k from n to 2 to the n. And so we use this, and transitivity gives us the following statement in the frame. So essentially on every input of length n, B outputs the answer that is not the most popular answer between those given by AI on inputs of length n. Okay, so so in other words, this means that AI agrees with B on no more than 1/2 plus some small epsilon fraction of inputs of length n. But our initial assumption was that AI agrees with B on 1 minus delta fraction of inputs of length n, and delta is smaller than 1/2. So we get a contradiction, and we get our time hierarchy for heuristic non-deterministic algorithms. So, are there any questions?
No, there is just a remark, a kind of cheating, because in a sense, because you say of heuristic algorithms, but you require still that the algorithms, this property of coincidence, is correct for every length. If you have some length, some small fraction of length wrong, this will not work, I guess. Yeah?
But this question, it's a matter of definition. Maybe.
No, you still need for all you have a long chain of you can amplify on each step, but somehow. So imagine you have some algorithm.
Some amplification trying to use main.
So imagine, for example, that the required is that not for all. It should be not for majority of strings of length n, but for majority of strings at most n.
Well, maybe with some now we have some problems with definition of what means majority of length. Maybe if we take right definition, we will just have to use cross simplification over some
different size. Okay, but.
I'm not sure I understand the question.
Okay, but
it's a question on the definitions. Forget that.
Let's move on.
Okay, under quite traditional definitions of heuristics, we have a time hierarchy.
But I have a central question. Why have you started with NP and not just with heuristic, deterministic polynomial time algorithms.
You mean why isn't, excuse me, why?
Is it sort of evident that
Why isn't this deterministic?
Is it sort of evident that hierarchy theorem holds for deterministic heuristic algorithms?
Yes, sure. Just on every input, produce simulate AI and output the opposite answer. You disagree with AI on every input of some particular.
Just the simple.
Yeah, it's just simple. Yeah, good question. So for deterministic algorithms, things are fairly simple, and even some strong statements can be proven.
What is very simple? Say it again.
Okay, so the question is, can I prove time hierarchy for deterministic heuristics? The answer is yes.
But how do we do that?
It's an exercise.
It's an exercise.
It seems that you explained that
It's very simple.
we still...
Sasha, we had non-determinism there, and that was the problem.
Okay.
Yes.
Okay, let's postpone.
Okay, in the case of deterministic algorithms, we don't need this big picture, and things are fairly simple. You just proceed like you did in the proof of just the usual time hierarchy for deterministic algorithms. And the last application of diagonalization that I'm going to speak about, but certainly it's not the last application of what I know, is its application to time hierarchies for slightly non-uniform algorithms. Let me switch from non-deterministic algorithms to probabilistic algorithms. This is because there's not much interest in proving time hierarchies for slightly non-uniform, non-deterministic algorithms. It's fairly simple. But it's not simple for probabilistic algorithms. Let me define what I mean by a probabilistic algorithm. So consider some probabilistic machine M. It has two inputs, X and R.
But it seems that you are considering just the usual definition.
Yeah.
I can skip it.
Okay, it's a PP. But let me just remind at least myself the usual definition.
Delayed diagonalization will just work also when you have non-uniformity?
Delayed diagonalization, no, but its extension, yes. Okay. So M receives X is the input and R is randomness. And we say that M recognizes L if on every input X, M outputs the value L of X with probability at least 2/3. And such machine, and we say that M recognizes L with bounded two-sided error. Now, I have to consider this definition just to say that this definition implies that not every probabilistic machine is good. The definition, if we say that M recognizes L, then by definition this means that on every input X we have that either M outputs 1 with probability more than 2/3, or it outputs 0 with probability more than 2/3. And we call such a machine good. But obviously there are machines that say, consider for example a machine that tosses a coin and with probability 50% it outputs 1, and with probability 50% it outputs no. So this machine doesn't recognize, according to our definition, this machine doesn't recognize any language. Its output is useless. It's just a random guess. So we cannot call such a machine good because it doesn't recognize any language. And the problem here that makes it difficult to prove a time hierarchy for probabilistic algorithms is that we have no enumeration, no efficient enumeration of good and only good probabilistic machines. We can enumerate probabilistic machines. They are just Turing machines with two inputs. But we cannot enumerate only good machines. So this is why a time hierarchy for probabilistic algorithms is just a conjecture. Again, we introduce some class of languages, and time hierarchy is conjecture. So let us see why should we have enumeration of only good machines. So, let me take enumeration of all probabilistic machines. So some of them are good and some of them are bad. And if we try to use that simple trick what we used for deterministic algorithms, if we construct B in the way that it simulates on input X, it simulates AI, and on the same input, and then negates the answer, then we have the following problem. If AI is bad, for example, it just tosses a coin on input X, then B also becomes bad. It also tosses a coin. Therefore, it doesn't recognize any language according to our definition, and we don't have a language that would justify this conjecture. So it seems somewhat technical, but I don't know no technical way to avoid this problem, and I also don't know how to change definitions so that this problem doesn't appear. So this is why we don't have time hierarchy for probabilistic algorithms. But let us see some interesting application of diagonalization. So let us try to prove time hierarchy for one-bit non-uniform algorithms. Those algorithms are quite similar to uniform ones, but they're somewhat different. So a one-bit non-uniform algorithm is just one-bit non-uniform probabilistic machine is just a probabilistic machine that with every input x of length n receives one bit of advice an. So if you are a machine with every input, you receive some additional bit that might tell you some very important information, and this bit is the same for all inputs of length of the same length, but may be different for inputs of different lengths. And again, the same machine M may be good or bad depending on advice. So with some advice M may be good, and with some advice it may be bad, may violate the promise to have its error bounded. And in what way can advice help us to prove time hierarchy then? Well, this one bit of advice may be used in order to tell B whether AI is good or bad. So let me define B in the way that on input X with advice 1, it simulates AI and outputs the opposite. And with advice 0, it doesn't do anything, just returns 0. So now we can set advice to 1 in order to tell our machine B that AI is good. Then B can simulate AI and stay good. And we also can set advice to 0 in order to tell B that AI is bad. Okay? Then B doesn't have to care about AI because AI doesn't define any language. And so it can just work arbitrarily out of 0 and stay good, in despite of the fact that AI is bad. However, time hierarchy for non-uniform algorithms is not that simple, because now AI, the interesting case is that AI also has advice. So it can, depending on advice, whether it's 1 or 0, AI may exhibit two different behaviors. Okay? So in some sense we have to provide two bits of advice, but we have only one. So this is why time hierarchy for a one-bit non-uniform algorithm is not simple. Let me just give you a flavor of how can we prove such time hierarchy. So let me choose a number of strings of different lengths, and as they are of different lengths, we can provide different advices on these strings to our machine B. Now let me consider input x1. It's input of very long length. It's a very long input. You may think it has a length 2 to the n. It's again a kind of a delayed diagonalization. And let me take one more input x2. Say it has, okay, you may think it's a little bit shorter than x1. Okay? And on input x2, let me define B in the way that with advice 1, which tells B that AI is good on x1, B simulates AI on x1 with advice 0. Okay? And with advice 0, B just stays good and doesn't care about AI. Also, let me take one more input of one more length, x3, And on input x3, b with advice 1 simulates AI on input x1, but now with advice 1. So you see, we use two different inputs just to take care about two possible behaviors of machine AI, because we have to diagonalize against machine AI whatever advice it receives.
But what if machine AI on one bit is good and on one other bit is...
Good question. Okay, so if AI
They have
is...
different lengths. They should have different lengths.
No, he's trying to diagonalize to AI both with the 0 bit of advice and 1 bit of advice.
Yeah.
Right.
And then use the real advice bit to tell you whether AI is good or bad. But AI could be good on one bit.
But this is
Sorry,
this,
my mistake.
this is easily answered
It's my
because
mistake.
we can use different lengths for x2 and x3.
I said it wrongly. I said that one bit of advice tells whether AI is good or bad. In fact, on this input, this bit of advice tells whether AI with advice 0 is good or bad. And on this input, bit of advice tells whether AI with advice 1 is good or bad.
Okay.
So if with advice 0 AI is bad, then B does nothing, because we give its the advice 0. And if AI with advice 1 is good, then we tell B that it's good. And
so you see that x3 is on the left of x2.
Yeah.
Probably this
Different lengths.
just means that they are different lengths.
does this
No?
answer? No?
Yeah, it answers,
Okay.
of course, but you haven't said it in advance, right?
Okay, so again, what we do is just a kind of delayed diagonalization, so I have to continue. I cannot stop just here. I have to produce some more levels in our tree. Okay, so now on input x4, we take care about AI on input x2 with advice 0, and on input x5 we take care about AI on input x2 with advice 1. And also we have input x6 and x7. And we proceed in a similar fashion. We obtain a tree. So, and we stop, then length of its leaves is they are logarithmical in the length of the root. Okay. So say x4, x5, x6, and x7 have length n, and x1 has length 2 to the n. And then we can use deterministic simulation in order to get desired negation, and well, from this idea we can get a time hierarchy for one-bit nonlinear form algorithms. But I'm not going to get into any more details. And just to finish my talk, I would like to mention what is known and what is unknown about time hierarchies up to this point. So, just to summarize what we know about time hierarchies for uniform algorithms. We know that they exist for any so-called syntactic model of computation. Just to say, there are syntactic models and there are semantic models of computation. And roughly speaking, semantic models are those models where we have to care about whether machine is good or bad. In syntactic models, we don't have to care. So in semantic model, we have some semantic constraints on machines. For example, the constraint that probabilistic machines should have its probability of error bounded. Okay, so it's a semantic condition. And we have to speak about good and bad machines, and this is semantic model. So we know time hierarchies for any syntactic model, like deterministic algorithms and non-deterministic algorithms, and so on. And we don't know whether time hierarchies exist for probabilistic algorithms.
But you have to skip the second line.
Wait a second.
Huh?
Two-sided error, one-sided error, zero-sided error, various interactive games, and so on. The only few like exceptions is IP. The class of interactive protocols, it has semantic nature, but we know that its computational power coincides with p-space, and p-space is syntactic, and in this case it's possible to derive a time hierarchy for interactive protocols. But
so the only known proof is by reducing to p-space.
Somehow, yeah.
Okay.
There is also one more class that uses Truda theorem, so that this power also coincides with the computational power of some syntactic class. Okay, For heuristic algorithms, we have seen that there exists a time hierarchy for heuristic non-deterministic algorithms. Also, it's an exercise to prove that there is a time hierarchy for deterministic heuristics. In the same fashion, we can obtain a time hierarchy for virtually any heuristic, but any model computations that is closed under taken majority. So we want to simulate some machine on polynomially many inputs and take the majority answer. And as to semantic models, only a few time hierarchies are known. We know time hierarchies for heuristic BPP, for heuristic Arthur-Merriam games and Merriam-Arthur. Actually, we can prove time hierarchy for probabilistic algorithms quite in a similar fashion what we did for heuristic non-deterministic algorithms. They are somewhat different, but the whole idea is the same. And joining these two results, we can get results for Arthur-Merriam and Merriam-Arthur games. And lastly, one may see that it's possible to prove that time hierarchy exists for virtually any model with one bit of advice. So we see that again. Okay, good.
Is this probably a different proof, not just the same?
It's this. Okay, I gave you the idea of how to prove time hierarchy for one bit non-uniform algorithms. This idea works for virtually every class. This is because, well, one bit for advice is a cheating. Okay. Thank you. If you have any questions, yes. I don't know, feel free.
So with the IP statement, would you? I mean, how fine coarse can you get your step if you have a little bit more time? I mean, it seems that you.
I'm not sure about how dense it is.
It's not going to be very good. I mean, well, I was trying to.
I'm not sure I can tell how dense the hierarchy is, but I know we have such time hierarchy.
I go to the simulation to piece and then back.
Yeah.
So I have very, very basic, informal question. So it seems that initially we consider the following problem. So we want to compute the behavior of given for deterministic machines, the behavior of a given machine after a given period. So we have two parameters: the size of the machine and the time needed to compute. So we want to make simulation of any machine in any given time. So we have function of two arguments. And there is a trivial way of computing this function, just by simulating this machine, which requires log of time plus size of a machine multiplied by the time and so on.
Yeah.
And then there is an informal claim that this is the best this way of computing of this function cannot be significantly improved, and this is somehow the source of all all hierarchy theory. So we have some function which is somehow for which we know that it cannot be computed faster, and then we just say that we can, from this function, combining combining the sizes of arguments, we do something. And then we get somehow hierarchy theorem. So is it what really happens?
That was a philosophical question, so you are allowed to give a philosophical answer.
Okay, but since it's a philosophical question, let me end this. The philosophical answer is just
maybe
silence. And I have a very simple question, but whenever I try to read your, without much success actually, but I tried to read your paper about hierarchy theorem, but it was a very clever paper. But the only thing I understood as an impression that you somehow used fixed point theorem, and now you did not mention fixed point theorem at all. So was my impression completely wrong, or you changed something in your?
What time hierarchy? You mean with one bit for advice?
No, I think that there was some general explanation that the late diagonalization somehow is now replaced by fixed point, or definitely there was something about fixed point, because this was very confusing for me. And at this point I gave up more or less, believing that you are probably correct, but too clever for me. So just, is it, but
Actually, no, I never wrote anything about fixed point.
Sasha, this is fake Konstantin's paper.
but maybe it will be the co-author. But did you claim that the paper which you wrote with co-authors also didn't have nothing about fixed point?
That was Lence's paper, Sasha. He wrote also a paper about one-bit advice. But you mixed, right?
No, but
I see no way to use fixed point theorem, but I believe maybe.
very strange. Okay.
Okay, I have a simple question. So, what about 2 bits of advice? Is it essential here that you have only one? Say 2 bits.
Well, the interest is to have as few bits of advice as possible.
Okay, okay.
It would have been nice to have 0. But
Okay,
we can't.
but for 2 bits everything works.
For
right?
2 bits, yes. If you have only 1 bit of advice, on the left hand side you can diagonalize against less time and 2 bits of advice, and any constant number of bits of advice. What you have to do, you just have to, you have 2 bits of advice
For
given to I,
with 1 bit of advice you can diagonalize against 2 bits.
and against 3 and more.
And
you just have to use more
and
edges.
poly over polynomial lines.
No.
Okay, and with how many bits you can diagonalize against polynomial number?
I don't know.
With polynomial, say,
I don't know.
no idea?
No idea.
So it's open also for in P/poly, if it is
Yes,
true or not?
as far as I know, yes.
Okay.
What's so open?
Whether hierarchy theorem holds for NP/poly, he claims it's open.
I say that I don't know.
But what is the correct version of hierarchy for non-uniform computations? For example, for circuits. If we allow bigger size circuits, probably we get more things recognized, more functions computable.
Probably.
But what is known? Maybe
But
somebody.
it is known that exponentially many it's enough.
So what is the right version of hierarchy for non-uniform computations? So
You can just do the straightforward diagonalization.
Nothing I see.
For deterministic.
So imagine we have, I don't know, circuit of size n square, and then circuit of size n square plus epsilon.
You can do
Just do the normal thing.
You can
by counting. Counting.
oh just by counting.
Right, yeah. Counting.
But how do you count? Because you don't know how many functions a circuit gives
You
same function.
consider very trivial functions that are durable by circuits of size n cube, right?
Yeah.
And 2 plus epsilon are functions that are defined that have only that many ones or something like that.
So you say that this is completely different thing, which has nothing. So in this case,
Counting is not even for diagonalization. These are just the same, another word for the same argument.
so you say that what is happening here is some perverse